627. Today we are going to do an introduction to Galerkin methods. And we will start with linear algebraic equations because they give you understanding. So let us say we solve a system of equations ax equals b. A is n by n, x is n by 1, b is n by 1. So there are n equations, n unknowns, and we'll assume A is invertible, which means the columns of A are linearly independent. Okay, x equals A inverse B, unique solution. Very good. What happens if m is greater than n, A is m by n, b is m by 1, x is n by 1. That means A looks like this, x looks like this, and b looks like this. There are m equations, n unknowns. This is an over determined system. We have more equations than unknowns, and in general there is no x that satisfies ax equals b exactly. Okay, assume again columns of A are linearly independent. Okay, so what we do in such cases, one of the things we can do is do a least squares solution. In a least squares solution, we say ax minus b is the error. Let us square that and let us minimize that over x. Okay, this is the same as saying minimize over x, ax minus b transpose ax minus b. It leads to the normal equations A transpose ax minus b equals 0. It leads to A transpose ax is equal to A transpose b. This is n by n invertible. Why is it invertible? If the columns are linearly independent, it will be invertible. Okay, so you may be familiar with this. If you are not familiar, please look it up. One way to think about it is to say the error is ax minus b, and this part here, let me make it with blue here, this part here says A transpose E equals 0. That means error is orthogonal to the columns of A. It's possible to have a nice geometrical view of this. And the geometrical view is, we realize that ax is actually a linear combination of the columns of A. The coefficients are x. What linear combination of the columns of A gives you something that is close to B. Okay, what linear combination of the columns of A gives you something close to B. Okay, so one way to view that now is to think of a lower dimensional picture. Think of this plane as having two vectors in it. These two vectors are the columns of A. They need not be perpendicular, but they are in the plane. The vector you want to approximate is this vector. This here is B. This one we will call A1, the first column of A. This one we will call A2, the second column of A. It should be clear that any vector in this plane, such as this one, can be exactly written as a linear combination of A1 and A2. And so it is useful to drop a perpendicular onto this plane and say this here is AX, the linear combination, and this here is E, the error vector, and this perpendicularity is A transpose E equals 0. So in the matrix case, in the linear algebraic equations case, the overdetermined system is clearly understood. Okay. Now let's come to a differential equation. So for example, we may have a differential equation ODE 1 plus x y double prime plus y equals 1. Y of 0 equals 0. Y of 1 equals 0. Y equals 0 is not a solution because of this 1 over here. So there is some non-zero solution. The solution of this differential equation may be in terms of special functions. We may not have an analytical solution, but there is some solution. YS, true solution. YA is an approximate solution which we write as I've used A here, but I hope you will not mind my using some coefficients. Let me say B, C. C1 phi 1 of x plus C2 phi 2 of x plus Cn phi n of x, where phi's are functions we choose. Okay, one of the things is we need a basis, right? So the solution we want to capture, this solution should in fact be expressible, at least if we take this to infinity, it should be captured. Otherwise, this approximation will fail. But if we take such a series and then we truncate it at n, so we cut it here and don't take any more, if we have a rational criterion for selecting these coefficients, we may get a good approximation. So how do we do that? We take this quantity which is supposed to be 0, we write this as 1 plus x y double prime plus y minus 1. Okay, into this expression which we want to be 0, we substitute y equals ya, and when we do this, it gives us a residual, something that has unknown coefficients c1, c2 up to cn. It has unknown coefficients. It cannot be 0 for any choices of these coefficients, because if it could be 0 for some choices of these coefficients, then we would have an exact solution. We don't have an exact solution. This is an approximate solution, so the residual is not 0. In an analogy with making it perpendicular like here, in an analogy with making, see, this error is now there, that is the residual now. Okay, making the residual perpendicular to each of the columns of A, the appropriate analogy here is we have to say residual, the dot product is understood to be phi k of x dx integrated from 0 to whatever the domain is. In this case, you know, the domain is from 0 to 1, right? So 0 to 1, we set this integral, which is the dot product of the residual with the basis function, equal to 0, k equals 1, 2, all the way up to n. This gives me n equations. I solve those equations and I get an approximation. Turns out rather good. This is a rather good approximation. This approximation method is called a Galerkin method after a Russian engineer called Galerkin. Okay, so it's rather good. If you do, this is related to a broader class of methods called weighted residual methods. These form the basis of the finite element method, but from here we will also eventually do something called harmonic balance for studying oscillations. That is later. Now let me show you this example using Maple. So I will go here and I will open my Maple window. That seems to be all right. I should probably move the window a bit here. That should be all right. So this is, I'm starting the calculation. Digits for numerical work, I've just put it at some large value. Here is my differential equation. I have brought that 1 over to the left hand side, you see. So this is the thing that is going to be 0. Maple has a command called dsolve. If it can solve the differential equation, it will. When I solve it in general, it tells me that it gives me a solution in terms of Bessel functions. Okay, so C1 and C2 over here, they are arbitrary constants in the solution because I have not put boundary conditions, and here is a particular solution. So the particular solution is y equals 1. The complementary solution is this part, okay, with the C1. All right. Now over here, note the syntax. I say dsolve, I have curly brackets to delineate, to mark what I am doing. Within the curly brackets, I have the differential equation and the boundary conditions, and I am solving for y of x. When I do that, that's my solution. What I do is I play a little trick. I want to pull out the right hand side, so I say substitute this equation into the expression y of x. That's just a Maple syntax trick. When I do that, it gives me the right hand side. I can plot the solution, y sol, I've given it a name, so when I plot it, that's the solution. You can see it goes to about minus 0.09. All right, so now over here, let me try this. I'll try with two shape functions. The phi's I am using are sine k pi x. So sine pi x, that is 0 here and here, matches the boundary condition. These are called essential boundary conditions. If you study the method more deeply, you will realize something about them, but I will not go into that now. Sine 2 pi x is another thing, 0 here and 0 here. In this way, if I take many such functions, I should be able to approximate this. Because this is a Fourier sine series, it actually gives me a basis, right? I know that from other analysis. So here is my approximation. In this picture here, I had used C1. You will notice I had used C1. but I have written A. Don't be confused. So this is my approximation. I have to find A1 and A2. All right. What I do is I'm creating the residual by expanding and substituting, and you see there is the residual. So it's a longish expression. Now what I do is I do the weighted residuals. So for k from 1 to n, I integrate the residual times sine k pi x, and I call that EQK. This is the thing that needs to be 0 for k equals 1 and k equals 2. Okay. Then this is my syntax for solving equations. So I have SS is, and just the solution will be given that name. Solve within curly brackets the sequence of equations EQK for k from 1 to n. Solve it for the sequence of variables AK for k from 1 to n, and it will give me this solution. These are the solutions. You can see that in analytical work the expressions can be a bit complicated, but Maple is doing it. We won't worry about it. So here is my A1 for approximate, and I'm substituting the numerical value into the expression YA, which was this. Let me remind you, this is YA. So I've solved for A1 and A2. I'm substituting that. That's my solution, and it's got these long coefficients. Don't worry, you will see that this coefficient, the coefficient of the sine 2 pi x, is a lot smaller than the coefficient of the sine pi x. When I plot the two solutions, one in red and one in blue, then you see that there is a difference, but it's not very bad. The solution is not very bad. When I plot the error, then you will see that the error is about 0.006. Okay, so that's what the error is with two terms. Now let me go back here and say I'm going to do this with 4 terms. So this residual is going to be a longer expression now. Then I will calculate these equations, but let me keep that also. So you will see that these equations are a bit long now. Doing this by hand would be difficult. When I solve this, they'll be long too. So I'll have these long expressions which are difficult, but when I evaluate and substitute, that's my expression. And you will see 0.09, 0.004, 0.0035, 0.0003, right? So they're going down. And then when I plot it, you will see that visually it is difficult to tell the two solutions apart. And when I plot this error, remember it was 0.006, but now it should be smaller, and it is 0.0015. Okay, I can go back and I can say maybe 8 shape functions. Now let me suppress the display of the residual. Let me suppress the display of the equations. Let me suppress the analytical expression for the equations, but let me look at the numerical answer. And you will see the coefficients are going down, 0.09, 004, 0035, and so on, 4 zeros. Okay, when I plot that, looks indistinguishable visually, but when I plot the error over here, remember it was 0.015 or so, but now it should be smaller. Yes, it is about 4 times smaller. Okay, so this is the introduction to the Galerkin method. Now I will come here and I will do the basis of harmonic balance is Galerkin. Well, basis as in justification, not as in basis in functional approximation. Okay, so example 1, x double dot plus x cube equals 0. Our intuition, insight, understanding, knowledge, these must enter the form of the solution we are posing. See, for example, if I have x double dot plus x dot plus x cube equals 0, every solution decays. Okay, so because that happens, I have no business looking for a periodic solution with harmonic balance. Okay, harmonic balance is for periodic solutions only. So this won't work, but this will. Every solution is periodic. Okay, this is conservative, does not dissipate energy. For example, x dot square by 2 plus x to the power 4 by 4 equals some constant. That is what this means. It is integrable. Okay, so this gives you some sort of closed curve, right? It gives you some closed curve in x dot space. Okay, so plane x dot, you'll get closed curves. They may not be circles or ellipses, but they're closed curves. Okay, go like this. Every solution is a periodic solution. What do I not know about the solution? Well, amplitude, indeterminate. It cannot be known. Why? Because every solution is a periodic solution, so naturally solution at any amplitude is possible. Okay, now how about time period? See, because for the differential equation example that we had over here, the domain was 0, 1. But over here, what is the domain? What is the time? The domain is 0, t. Let us say t is equal to 2 pi over omega. Okay, so this omega is not known but must be found. Now the point is, this omega actually depends on A. A is the amplitude. So if the amplitude is A, then omega depends on A. Okay, so here's what we do. We say it's a periodic solution. I can expand it in a Fourier series. So when I expand some periodic function in a Fourier series, what I have is that's the basis, right? So I'll have something like A0, that's a constant term, plus the sum from k equals 1 to infinity of ak cosine, and I have to be a bit careful here, when t let's see, k t 2 pi over capital T. Okay, why? This is the Fourier series. We will discuss this very soon. N equals 1 to infinity bk sine 2k, 2k pi t over capital T. Okay, what we have to note here is when this t goes from 0 to this capital T, this argument goes from 0 to 2k pi. That is what will give me the Fourier series. So 2 pi, 4 pi, 6 pi, and so on. Okay, now this is the full expansion, but I will use my knowledge of this system, right? My knowledge of this system tells me that I can start time like this, so that it sort of is just a reflection. I can start at 0. That means 0 mean and cosine is not there. Okay, so for this problem I can just use a sine series if I wish, and I can say x is equal to a sine omega t, because 2 pi over t is omega. Okay, a1 plus a2 sine 2 omega t plus a3 sine 3 omega t plus an sine n omega t, and I truncate there. Stop. Okay. Now, there are further symmetries in the problem. Because of this conservation, what happens is when x is increasing or when it is decreasing, when it reaches a certain value, this is a constant, this x to the power 4 is a constant, therefore x dot is a constant. Going up and going down are the same. This means that over here whatever the slope is and over here whatever the slope is, the magnitude is the same. Okay, so there are such symmetries which I can use to convince myself that this one will be 0, this one, sorry, this I don't know, depends on n or odd, only odd harmonics are present. Okay, so as I had shown in a discussion earlier, but over here also, what we will do is we will take x double dot plus x cube as the differential equation. Into that is what has to be 0. Into that we will substitute x equals a1 sine omega t plus a3 sine 3 omega t, for example, and that's a two-term approximation, and that will give me a residual which cannot be 0 for any choice of a1 or a3 or omega. All right, and then what I will do is I will then multiply, I will residual dot sine omega t dt from 0 to 2 pi over omega. Okay, and I'll set it equal to 0. Similarly, I will do residual times sine 3 omega t dt, same period, 0 to 2 pi over omega. Let me separate this over here so that you don't get confused. Okay, so this we set equal to 0, and we can't do more. We have these two, only two basis functions are there. The residual has to be made orthogonal to those two basis functions, and that is what will give me this, and this will give me two equations. These equations, let me remind you, these two equations involving a1, a3, omega. Why is that? Because omega depends on the amplitude. The amplitude is fundamentally indeterminate. Okay, so I can say for this omega what are a1 and a3, then I can solve that. Or I can say given a1 what is a3 and what is omega, we can do that. So some examples of this we will be seeing later, right? That sort of takes up all our space and time, but over here let me just add one small thing. Other problems are possible. So for example, if I have x double dot plus, let us say 0.1 x dot, now this is damped, plus x plus 0.4 x cube equals f sine omega t. Omega is known, f is known. Now this has damping, so there will be some transient. Initial condition effects will eventually disappear. This will lead to a steady state solution. That solution, if I do one frequency only as an approximation, I will say x is equal to a sine omega t plus b cos omega t. Okay, how many unknowns now? 2. I substitute this expression into this equation and I get a residual r. I take the dot product r sine omega t dt 0 to 2 pi over omega, set it equal to 0. That's like pulling out just the sine omega t term. Similarly, I do another one, 0 to 2 pi over omega or cos omega t dt equal to 0. These are my two equations. These two equations I solve for A and B. So this is a different type of approximation. You will notice that the form that I am choosing depends on my understanding of the problem. So in later lectures we will see other examples of such things, and hopefully they'll become clearer.